From this video onwards, we are going to start discussion on generalized linear models. In linear models that we have already seen, we had this box diagram. We had some inputs. They could be categorical or continuous. They were fed into our black box or green box. We had some random error coming in, and using all this stuff, the output, the response that came out was a continuous thing. That was a linear model when we modeled this inside thing as a linear function. However, this did not allow the situation where this output is a discrete quantity. If that is a discrete random variable, then we shall have generalized linear model. Instead of jumping right into the math, let us learn the subject the way it was originally created. It was created by someone called D.J. Finney, a statistician who is possibly more appropriately called a toxicologist. Now, a toxicologist works with poisons and works with things like estimating the strength of some poison. One way of measuring the strength of a poison is by what is called its lethal dose. Say, for example, if I ask whether potassium cyanide is a stronger poison or arsenic, then one way of quantifying the fact that potassium cyanide is a stronger poison is by saying that you need only a very little amount to kill a person, while for arsenic the corresponding amount will be much larger. Now, Mr. Finney was trying to get a numerical value for this lethal dose, the minimum dose of the poison that is required to kill. Now, he was well aware that while the lethal dose depends on the particular poison, it also depends on what you are trying to kill. Namely, you talk about lethal dose of a poison for a particular population. And even then, for one person to another person, the amount might vary. The amount that will kill me may not be enough to kill you. Similarly, if you are working with mice, as Mr. Finney was working with, the amount required to kill one mouse may naturally differ from the amount required to kill another mouse. So the lethal dose of a particular poison for a particular living creature is naturally like a random variable, much like our height, weight or blood pressure are considered random variables. So what Mr. Finney did was to think of this as random variables. So you have got, say, quite a few mice, say n mice, and for each one of them you find out the corresponding lethal dose, and then you will just take you are basically getting a random sample, and that random sample will be this x1 to xn, and he assumed that they follow some Gaussian distribution. The entire discussion is not tied down to Gaussian distribution, but that's the assumption that D.J. Finney used. So normal mu sigma square, in that case he can estimate mu and sigma square once he measured this x1 to xn, and in parlance of toxicology, mu hat will be the potency of that poison and 1 over sigma square hat will be the reliability of the poison. So is there too much fluctuation among the lethal doses of different types of or different members of the population? So D.J. Finney's aim was to carry out this exercise. This might seem like a pretty simple thing. You just get a sample x1 to xn and then estimate mu and sigma square. What can be simpler? So you might think that we can ideally carry out an experiment like this. What we do is we just take n mice, n is the required sample size, and here is one of them. Now what you do is you start applying the poison slowly. So you start applying the poison, push the syringe down, still it is living, push the syringe down further, and the mouse is dead. So at this point you just record the particular amount of poison that you have applied from the reading of the syringe, and that gives you your x1. Now take the next mouse, which should be as identical as possible to the first mouse in terms of age, etc. And you do the same thing. You do it n times, and as a result you get x1 ... up to xn. Much like measuring blood pressure of n patients or height of n students. But unfortunately, this simplistic idea just does not work. The reason being that, unlike measuring blood pressure or measuring the height, death is not a clearly discernible event. When you start applying the poison to the mouse, after a stage it goes into a coma state, and it is difficult to understand whether the mouse is living or dead. So you have to stop the experiment, take the mouse to a different table and do some time-consuming experiment to figure out whether the mouse is really living or dead. Say this takes 10 minutes. Now within these 10 minutes, if the mouse is not dead, its purgatory system is working at a tremendous rate and is removing much of the poison from its blood system to its urinal bladder. So if after 10 minutes you figure out that the mouse is not dead, you cannot haul the mouse back into the first table and continue with the experiment, because now the effective amount of poison inside the blood system of the mouse has changed. As a result, all that you can really hope to get from such an experiment is that you apply a fixed dose, then look at the mouse. Either you can see it is clearly living or it's in a comatose state, in which case you have to carry out that experiment and see whether it is really living or dead. You cannot continue that experiment any further. For a dose, you only know if after the dose the mouse is living or the mouse is dead. You cannot observe those Xi's directly. Mathematically, the situation is like this, that suppose the true lethal dose for that particular mouse is X and you have applied a dose B. Now you may either see that the mouse is dead or the mouse is alive. In that case, all that you can conclude is this: if the mouse is dead, the only thing that you can conclude is that X must be less than or equal to D. If the mouse is alive, then you can say X is greater than D. Nothing more than this may be said. So you cannot observe X directly. X is what is called a latent variable. You cannot observe it directly. Now in order to cope with this situation, that is, you want to estimate mu sigma square but you cannot observe the X size directly, DJ Finney devised a new type of data collection which is commonly known as bioassay.